Well, hello. Welcome to Wish Teachers. And here we are trying to read two books. One of them is Deep Reinforcement Learning of Grokking, and the other is Hands-on Machine Learning for now. And yeah, we'll try to cover one chapter every week if possible. And it's finally the time. So we're finally starting from chapter 1 of the book. Let's first see what we are supposed to have in the future. So the book starts with a foreword, preface, acknowledgement, and stuff like that. But then from the first chapter, we have an introduction to deep reinforcement learning, which covers some basics and terms that are necessary for the rest of the book. For the second chapter, we have mathematical foundation of reinforcement learning, which basically talks about MDPs and what are the specific parts in an MDP. In chapter 3, we have balancing immediate and long-term goals. Chapter 4 is balancing the gathering and use of information. 5 is evaluating agents' behavior. And 6 is improving agents' behavior. And 7 is achieving goals more effectively and efficiently. So chapter 1 to 7 are more like not deep reinforcement learning, but from chapter 8, the deep part starts to work. So chapter 8, we have introduction to value-based deep reinforcement learning, which has like NFQ and some other algorithms. In chapter 9, we have more stable value-based methods. It goes with DQN, DDQN. And on chapter 10, we have sample efficient value-based method, which it's dueling DDQN and prioritize experience replay. And we have policy gradient and actor-critic methods on chapter 11, and for chapter 12, advanced actor-critic method. And on chapter 13, we will see what comes next. But without further talking, this book does cover so many stuff inside it, and it's kind of a heavy book. You will need a kind of prior knowledge on mathematics and maybe a bit of Python, like actually a good amount of Python. But the thing is that this book uses Torch and PyTorch, so it's not with TensorFlow. So just keep that in mind. It is Torch. But without further talking, let's just dive right into chapter 1. I'll try to be as clear as possible and explain the concepts as we go through the book. But if you have any questions, just ask them in the comment. I'll try to reach to them as soon as possible. So, chapter 1, Introduction to Deep Reinforcement Learning. What is the first part? It says that in this chapter, you'll learn that what deep reinforcement learning is and how different it is from machine learning approaches. And you'll learn about the recent progress in deep reinforcement learning. It's more like a kind of a history and some basics. This chapter is like that, but it's still an important thing to learn the foundations. You will know what to expect from this book and how to get the most of it. And on the first one, we have kind of a quote from Claude Shannon, which was the Shannon method. I don't know if you are familiar with it or not, but he kind of like made this entropy things in machine learning. And he says that I visualize a time when we will be to robots what dogs are to humans, and I'm rooting for the machines. Okay, so let's just start. So basically it mentions that humans naturally try to pursue happiness in life, and any rewarding moment is the thing that we try to seek. And these feelings are kind of like the reason that we exist. And it talks about intelligence. It says intelligence is defined as the ability to acquire and apply knowledge and skills. And basically it mentions that in this book we'll learn about an approach called deep reinforcement learning, which is kind of like creating a computer program that can achieve goals that require intelligence. But it was kind of like based on the way that humans try to achieve goals. So we try to maximize the reward that we're going to get, and reinforcement learning is something similar. So what is deep reinforcement learning? It mentions that deep reinforcement learning, or DRL, is a machine learning approach to artificial intelligence. And it mentions that the distinct property of DRL programs is learning through trial and error feedback, that's simultaneously sequential, evaluative, and sampled by leveraging powerful nonlinear function approximation. So pay attention to these three words: sequential, evaluative, and sampled by some function approximation. So these three words will come handy later in the book, and it will explain what the author means by sequential, evaluative, and sampled. So the goal of this book is just we will understand deep reinforcement learning and can kind of like implement it on code after our understanding. So we have deep reinforcement learning as a machine learning approach to artificial intelligence. Just think about the sentence is a machine learning approach to artificial intelligence. And it mentions that AI, or artificial intelligence, is a branch of computer science involved in the creation of computer programs capable of demonstrating intelligence. Traditionally, any piece of software that displays cognitive abilities such as perception, search, planning, and learning is considered part of AI. Several examples of functionality produced by AI softwares are the pages returned by a search engine, the route produced by a GPS app, etc., etc. So the subfields of artificial intelligence is so wide. It's like even logic, we have robotics, we have search, computer vision, and stuff like that. And all of these are kind of like a subfield from artificial intelligence. These are some of the most important areas. We have expert systems, which kind of like are important, planning, NLP, perception, and stuff like that. And it says that all computer programs that display intelligence are considered AI, but not all examples of AI can learn. So pay attention to that, because they said that there's a statement that says even if you put an if statement in your program, it's kind of an AI, because you're just putting some intelligence to your machine. But still, that doesn't mean that your machine can learn. So machine learning, or ML, is the area of AI concerned with computer programs that can solve problems requiring intelligence by learning from data. So we have the data here. We need some data. Machine learning is those programs that can get intelligence by this data. So they will see the data, and then after learning the data, they can solve other problems. There are three main branches of ML. We have supervised, unsupervised, and reinforcement learning. So this is kind of like artificial intelligence, the big one, the big oval here. And then we have machine learning under it, and we have three branches: supervised learning, unsupervised learning, and reinforcement learning. And they have some kind of mutual parts. So we have some mutual parts for supervised learning and reinforcement learning. And like this is the most challenging part, maybe the hardest thing to think about, but we have even some mutual parts between all three of these parts. So it mentions that they aren't mutually exclusive. Okay, so to have kind of a description of each of these branches, we have supervised learning, or SL, which says is the task of learning from labeled data. So we pay attention to the word label here. So supervised learning is the task of learning from labeled data, and in supervised learning, a human decides which data to collect and how to label it. So the human decides which data to collect and how to label it. The goal of supervised learning is to generalize. Like it says that a classic example is the handwritten digit recognition application, and like we have this MNIST data set that is made by lots of handwritten digits, like 1, 2s, etc. And then you, for example, you try to train your algorithm based on these data and these images, and then you want it to be generalizable. So if you put another picture, for example, a picture of 8 to it, it doesn't give you the wrong answer. It says that it's an 8. This is the goal. And unsupervised learning, or UL in this book, is the task of learning from unlabeled data. So we have learning from unlabeled data. We have a bunch of data that is actually unlabeled. Even though data no longer needs labeling, the methods used by the computer to gather data still need to be designed by a human. The goal of UL is to compress. So a classic example is clustering. We say clustering, and it says computer segmentation application, that a human collects the customer data and then trains a model to group customers into clusters. And these clusters compress information, uncovering underlying relationship in customers. Another example of unsupervised learning could be images, like Google Images, the way that you search for something and then it provides some, without you labeling it, like as a flower or something like that, but it provides you with some much more similar images to your main image, so that you have a cluster of these images, something like that. And then we have reinforcement learning, which is a task of learning through trial and error. In this type of task, no human labels data and no human collects or explicitly designs the collection of data. And the goal of RL is to act. Okay, so the goal of RL is to act. And a classic example of RL is a Pong playing agent. The agent repeatedly interacts with a Pong emulator and learns by taking actions and observation and observing their effects. So if I want to show you, we have the Pong of Atari, which is, this one. This is the game of Pong. So there are two different agents and then there's something that goes and comes. It's like they're playing a ping pong. It mentions that a powerful recent approach to ML. So we have then we have deep learning. And it says that a powerful recent approach to ML called deep learning, or DL, involves using multi-layered nonlinear function approximation, typically neural networks. So we have deep learning, which has some layers of neural networks, and this is kind of like a solver, maybe I can say a solver, a recent approach to machine learning, that using it helps all of these three environments to become much better. So we have deep learning here, which has some similar parts, like some mutual parts with all of these three parts. And one of them is the deep reinforcement learning, which is basically the intersection of RL and DL. And it mentions that DL is a collection of techniques and methods for using neural networks to solve ML tasks. And whether it's supervised learning, unsupervised learning, or reinforcement learning, and DRL is simply the use of DL to solve RL tasks. And it mentions that DRL is an approach to solve a problem. Okay, on the next line, but first let me make sure that it's working. Yes, it is. All right, so the next line mentions that deep reinforcement learning is concerned with creating computer programs. So this is important. Like in DRL, the goal is to create a computer program. DRL is about complex sequential decision-making problems under our uncertainty. We'll reach to this sentence next chapter much more deeply, but just pay attention to the words. We have complex, sequential, and we have complex, sequential, decision-making problems and under uncertainty. But this is a topic of interest in many fields. For instance, it mentions that control theory studies ways to control complex known dynamic systems. In control, the dynamics of the system we try to control are usually known in advance. So we have control theory, which has some similarities with RL, and then we have operations research Another instance also studies decision making under uncertainty. So in operations research, we do study decision making under uncertainty, but problems in this field often have much larger action spaces than those commonly seen in DRL. And then we have psychology, which studies human behavior, which is partly the same complex sequential decision making under uncertainty problem. So we have reinforcement learning, which has some similarities with options research and optimal control. In optimal control and reinforcement learning, we normally have model-based methods, and in operations research and reinforcement learning in mutual part, we have large action space methods. So it says that all of them study complex sequential decision making under uncertainty, and then reinforcement learning and optimal control both contribute to the research of model-based methods, and reinforcement learning and operations research both contribute to the study of problems with large action space. Okay, so then it mentions that in DRL, these computer programs are called agents. So we said that it's concerned with creating computer programs. In DRL, these programs are called agents. So basically, an agent is the decision maker. Just the decision maker, and that's important to pay attention to. So the agent is the decision maker only and nothing else. That means if you are training a robot to pick up objects, the robot's arm isn't part of the agent. Only the code that makes decisions is referred to as the agent. So for better explanation, we have this page which says deep reinforcement learning agents can solve problems that require intelligence. So here we'll have a better explanation here, but first let's talk about the environment. The environment is basically everything outside the agent. So we have agent, anything else is the environment, which the agent was the code, the brain, which decides the decisions, the decision maker, and anything outside the agent is the environment. So everything the agent has no total control over. And again, it says that imagine you are training a robot to pick up an object. So we have a robot, we want it to pick some objects here. And here the code is the agent, just the code, which is the decision maker. And anything else is considered as the environment. So even the robot's arms and actuators, because they will have some noise and we do not have the full control over them, they are part of the environment and they might be noisy and stuff like that. So everything else is the environment. So it means that the robot's arm is also a part of the environment because it is not part of the agent, and even though the agent can decide to move the arm, so the code can tell the robot's arm to move, but the actual arm movement is noisy, and thus the arm is part of the environment. And then it mentions that the decision maker, the agent, can only have a certain role and a single role, making decision. Everything that comes after the decision gets bundled into the environment. Okay, so on the next part we have states versus observations. So the environment is represented by a set of variables related to the problem. For instance, in the robotic arm example, the location of these objects and velocities of the arms and the location of the arm would be part of the variables that make up the environment. So this set of variables and all the possible values that they can take are referred to as the state space. So state space is basically some of the variables that make the environment. A state is an instantiation of the state space. So this is a state. We also are going to have a more explanation on these concepts, but just for the beginning chapter, a state is an instantiation of the state space, a set of values the variables take. But the thing is that the agents often don't have an access to actual full state of the environment, and that's a challenge. The part of a state that the agent can observe is called an observation. And the fact that the states and observations are not usually the same, and the agent don't have the access to the full states, brings something called partial observable Markov decision problems, which we will learn about later. But just know it in your mind that the states are not the same as observations, and we do not usually have access to full states. Sometimes we do, sometimes we don't, but it's not usually the case. So observations depend on the states, but are what the agent can see. For instance, in the robotic arm example, the agent may only have access to camera images, while an exact location of each object exists. The agent doesn't have access to this specific state. Instead, the observations the agent perceives are derived from the states. So check this. We have the states, which is just like the true locations and every single important thing that makes this environment, for example, the locations of these objects, but the observation will be just the image, just an image, and even some border images that change and make some changes in the location. So this is the observation that the agent receives. It doesn't have access to these numbers, the exact numbers. Okay. So at each state, the environment makes available a set of actions that the agent can choose from. So the goal of RL, as we mentioned earlier, is to act. So at each state, the environment makes available a set of actions that the agent can choose from. The agent influences the environment through these actions, and this is important too. Like maybe this is the difference, one of the major difference of RL with other machine learning approaches, that the agent can influence the environment. The environment may change the states as a response to the agent's action. And the function that's responsible for this mapping is called the transition function. So the transition function is basically a mapping function that provides a state to the next state in the environment. And the environment may also provide a revert signal as a response. So this is something important as well, and some key point in RL. The function responsible for this mapping is revert function. And then the set of transitions and revert functions is referred to as the model of the environment, which sometimes we have access to and sometimes we don't. So basically, this is a reinforcement learning cycle. We have the environment and then we have the agent. Environment has some states that from one state to the other state happens by the transition. The agent takes some actions. The environment changes its state based on the action, and then some observation and revert are sent to the agent. And based on those observation and reverts, the agent improves. So it mentions that, why is this like this? Okay. So it mentions that the cycle begins with the agent observing the environment. This is how the cycle begins. The agent uses this observation and revert to improve at the task. And it then sends an action, so it chooses an action and sends the action to the environment to control it in a favorable way. And then finally, the environment transitions and its internal states changes as a consequence of the previous states and the agent's action. Then this cycle all repeats. So we have again observation, improvement, action, environment, states. So the environment commonly has a well-defined task, and the goal of this task is defined through the revert function. This is important too. So sometimes, like most of the time, we have a revert function, and the goal that we are trying to achieve is by maximizing this revert function. And this is the task that we want to do in the environment. The reward function signals can be simultaneously sequential, evaluative, and sampled. To achieve the goal, the agent needs to demonstrate intelligence, or at least cognitive abilities commonly associated with intelligence, such as long-term thinking, information gathering, and generalization. The agent has a three-step process: interacts with the environment, the agent evaluates its behavior, and the agent improves its response. Can be designed to learn mappings from observations to actions called policies. So policies are mapping from observation to actions. The agent can be designed to learn the model of the environment on mappings called the model, and can be designed to learn to estimate the reward to go on mappings called value functions. And these are three key versions that a reinforcement learning problem can have. So either we are trying to learn policies, which are the mapping of observations to actions, or we are trying to learn the model of the environment, which is like the mappings of the states to the next state, how the environment works basically. And sometimes we are trying to learn the value function, which is like the rewards that we are supposed to get in the future, like if we go to the end of the future, the estimated reward. So here we are. On the next page, it mentions that deep reinforcement learning agents improve their behavior through trial and error learning. This interaction between the agent and the environment go on for several cycles. Each cycle is called a time step. So each cycle is called a time step. At each time step, the agent observes the environment, takes action, and receives new observation and reward. So each of these full cycles are called a time step, and at each time step we have observation, action, and new observation. So the setup, this state, action, reward, and the new state is called an experience. It's usually a tuple, something like this, a tuple of experiences, which is like a state, action, reward, and next state. So this is experience tuples that we have in time step T. We have an agent and the environment. We are in the state S. Then the agent takes action A, receives reward R, and here we are on state S prime with the reward R prime. So on a state T plus 1, and it goes on and on and on. So the experiences would be like T, S A, R prime, S prime, T plus 1, S prime, A prime, R zigone, S zigone, and stuff like that. The task the agent is trying to solve may or may not have a natural ending. So sometimes we have a natural ending, sometimes we don't. For example, there are some problems called bandits, which we will learn, but they are just one state. Like consider this, that you go to a casino and then there is this bandit machine, slot machine, that there is just one action to take. Like you just pull the arm and you receive something. That's all. There's just one state there. There's just one non-terminal state actually, but yeah, it's just one thing. And it has a natural ending. But there are some other versions that we do not have a natural ending. For example, consider a game that the goal is just to maximize the score that you get. Like it won't end at all, like you're just going and going, something like this. Or just another game, maybe games like Sims, for example, but there is no natural end. Like you can keep it on forever and ever. Obviously there are some ways to fail or die, but still it can be infinite. And then tasks that have a natural ending, such as games, are called episodic tasks. As an example, think about a breakout game where there is a paddle and then there's a ball which goes and the goal is just to remove all the bricks on top. So it is called like an episodic tasks. In each episode you have something. There's a goal to achieve. And conversely, tasks that don't have a natural ending are called continuing tasks, such as learning forward motion. Also, this one is a good example too. Think about that you are trying to learn to just go. For example, you're trying to teach your robot. Okay, your robot is trying to learn how to just go forward. There is no natural ending there. Your robot will just go forever, but the goal is to learn how to do it correctly. The sequence of time steps from the beginning to the end of the episodic task is called an episode. Agents may take several time steps and episodes to learn to solve a task. Agents learn through trial and error. They try something, observe, learn, try something else, and so on. So here we will have a good example of how does trial and error work. But first, deep reinforcement learning agents learn from sequential feedback. So one of the key terms, we have sequential, we have evaluative, and then we have sampled. Let's see what does sequential mean here. It says that the actions taken by the agent may have delayed consequences. For example, on chess, like you play and play and play, and at the end it will be revealed that you will win or lose. So you won't know what action was responsible for your winning or your loss, for example. And this is very important key, which is called credit assignment. And it's the same like in your normal life. For example, you achieve a very good success, but you don't know what action specifically led to that experience. Like, for example, I don't know, there are lots of examples, like you win a trophy, but you are not sure which one of these actions that you did were responsible. Like you stayed late at night, you were studying a lot, I don't know, you didn't go to parties and stuff like that. Like there were a combination of actions, but which action was responsible for this winning trophy? Anyway, let's read. So the reward may be sparse and only manifest after several time steps. Thus, the agent must be able to learn from sequential feedback. Sequential feedback gives rise to a problem referred to as temporal credit assignment problem. That's the same with the chess, for example, and the things that I mentioned. Like you lose a chess game, but you may be very great to the middle, like until the middle of the game you have been playing awesome, but then some specific move has made it all wrong. But which move was that? Then at the end of the game you'll receive a -1, maybe reward of losing. And that's important. This is a very open area for research in reinforcement learning. The credit assignment problem. Which action takes the credit? The temporal credit assignment problem is the challenge of determining which state and or action is responsible for a reward. When there is a temporal component to a problem and actions have delayed consequences, it's challenging to assign credit for rewards. For example, think about this specific picture. We have the agent that mentions that, okay, the environment says you are in a state 0, and then it takes action A, it receives a +23. You are in a state 3. Nice, action A again, please. And then it's still stuck in state 3, but then it receives a -100. And it says, oh my god, get me out of here. And it takes action B, and it says, sure, another -100, and still on state 3. Now it is thinking. It says that, was it taking action A in state 0? That is to blame for the -100. And it mentions that, okay, choosing action A on state 0 gave me a good immediate reward, but maybe that's what sent me to state 3, which is terrible. Or maybe it was because it took action A again, maybe just taking it 2 times in a row is problem, or anything else. Like it could be anything. It doesn't know, the agent doesn't know which action to blame for these negative 100. And it mentions that in chapter 3 we'll study this sequential feedback isolation, and it says that your program learns from simultaneously sequential, supervised as opposed to evaluative, which we'll learn about later, and exhaustive as opposed to sampled feedback. So in chapter 3, we'll study the way that the agent learns from just sequential and supervised and exhaustive feedback, not evaluative and neither sampled, for chapter 3. And then we have deep reinforcement learning agents learn from evaluative feedback. Now, what is evaluative? It mentions that the reward received by the agent may be weak in the sense that it may provide no supervision. The reward may indicate goodness and not correctness, and that's important. The reward indicates goodness of the action, but not necessarily correctness of it, and that's something to pay attention, like maybe a difference of RL and SL, that having a +1 reward may show that, okay, this action is good, but that doesn't mean that it's correct, because you may have another action that will give you a +1000, and it's still a show of goodness, like, because there might be another action that give you a +2000 and stuff like that. So it may contain no information about other potential rewards. Thus, the agent must be able to learn from evaluative feedbacks. Now, evaluative feedback gives rise to the need for exploration. The agent must be able to balance the gathering of information with the exploitation of current information. And this is called the exploration versus exploitation trade-off. And in chapter 4, we'll study more on this evaluative feedback in isolation. So the program will learn from feedback that is simultaneously one-shot as opposed to sequential, and then evaluative and exhaustive as opposed to sample. So in each chapter, we'll just pick one of these words and kind of like play with them to see what they mean and how the agent acts while tries to learn from these type of feedbacks. And as an example of exploration versus exploitation, we have this. Like the environment mentions that you are in a state 0, and then the agent is like, okay, I'll take action A. And then it says you got a +50, you are in a state 0, and it gets action A again, and gets 20, still in state 0. So lots of like positive rewards by taking action A in state 0, but the agent mentions that, okay, I have received lots of rewards, now let me try action B. But it receives a +1000 when it tries action B, and it's like, okay, action A doesn't seem that rewarding after all. I regret choosing action A all this time. So next we read about that deep reinforcement learning agents learn from sampled feedback. So we had sequential, we had evaluative, and now we have sampled. It mentions that the reward received by the agent is merely a sample, and the agent doesn't have access to the reward function. So we don't know the reward function, we just receive one sample of it. Also, the state and action space are commonly large, even infinite. So trying to learn from sparse and weak feedback becomes a harder challenge with samples. Therefore, the agent must be able to learn from sampled feedback, and it must be able to generalize. And one way to do so is by neural networks and function approximation. So it mentions that learning from sampled feedback is just like you are in a state 0, 1, 0.1, 1.3, negative 1.2, 7.3. Like there are so many variables here. And it says, what is that? Okay, I'll take action A, and then it got a +1 in another weird 4 combination of 4 digits of states. And then it's still like it keeps on, and it has no clue, the agent, and it mentions that I have no idea what's going on. I need function approximation because like we have a vector of states, so we need a function approximation. Perhaps I get a fancy deep neural network. And it mentions that agents that are designed to approximate policies are called policy-based. So the agents that want to approximate policies. Agents that are designed to approximate value functions are called value-based. And then the agents that are designed to approximate models are called model-based. And then there are agents that are designed to approximate both policies and value functions. These are called actor critics. We'll learn about them, all of them, in the future chapters as well. Okay, so next we are here, which says that deep reinforcement learning agents use powerful nonlinear function approximation. So neural networks are data hungry and challenging to interpret. One of these like nonlinear function approximations via neural networks. Also, it mentions that some of other algorithms like use decision trees or SVMs, but usually it's neural networks for deep RL. Like deep part is actually the deep part is actually referred to the neural networks. So it says that they are normally data hungry, and just it's important to keep it in mind that we need to feed them lots of data if we want to get a good response from a neural network. But just pay attention to this one when you are trying to solve a problem. But regarding this, neural networks are among the best function approximation available versions today, and their performance is normally the best. Okay, so this is like a simple feed-forward neural network that we have an input and output layer, and then there are some hidden layers. Like here we have 3 hidden layers. And yeah, you have to be familiar with these for this book, but I think there will be some more explanation on the way. But even if you are not, I'll try to cover like the basics of it at least. But yeah, just know that we use neural networks for deep reinforcement learning for now. And then it says artificial neural networks are multi-layered nonlinear function approximations, loosely inspired by the biological neural networks in animal brains. And an ANN isn't an algorithm, but it's a structure composed of multiple layers of mathematical transformations applied to input values. And it mentions that from chapter 3 to 7, there's only problems with agents learning from exhaustive as opposed to sampled feedback. And then from chapter 8, we start the DRL, so the agents will learn from sampled feedback. And we'll use neural networks then. Okay, so just remember that DRL agents learn from feedback that's simultaneously in DRL. So we are learning from feedback that's simultaneously sequential, evaluative, and sample. Okay, so now we have reached to some history. We have the past, the present, and future of deep reinforcement learning. I'll try to just read through and just give you the gist in here. So it says that the hype surrounding AI is actually productive. People get interested, but right after that, when it's time to put in work, hype no longer helps, and it's a problem. Although the author mentions that I like to be excited about AI, I also need to set realistic expectations. But rather than that recent history of artificial intelligence and deep reinforcement learning, it just mentions that there is lots of hypes around AI, like on year, like at first, like we had some hype, and then there was a disillusion that the hype went over, and then it happened, so there was another hype, but then the AI winter happened and it kind of like went down. And here from 2000 to present, like the AI funding is going higher and higher, and the author is just having questions about whether it's another hype or are we going to just keep on. And yeah, AI has followed a pattern of hype and disillusion for years. What does the future hold? Well, actually, like we are past this era. Like I think this book was published in 2017, if I'm right. So it is still high. So maybe it is high, maybe it's not, but it's probably not because we are reaching to some extreme levels of AI recently. And then it mentions about the Turing test, which was made by Alan Turing, which is like if a person cannot distinguish between AI and another human, that AI is considered to be like very, very intelligent. Okay, so then we have just deep reinforcement learning, progress in deep reinforcement learning. And one of the very important part, like it says that RL probably started from 1990s with TD Gammon, which didn't necessarily use deep, but it kind of like, it was like not a deep network, but it's the beginning of the RL. So TD Gammon architecture, like it's something like this, it tries to play and learn this game, and the output was predicted probability of winning given the current game state. And then it mentions some other background and history in DRL, like in 2004, Andrew and G and et al. Developed an autonomous helicopter that taught itself to fly stunts by observing hours of human expert flies and etc. But then, like one of the most important things that happened on AI was the DQN algorithm, which in 2013 and 2015, Min et al. Published a couple of papers presenting the DQN algorithm. This was really like a revolution in DRL because DQN was like the first algorithm that could learn to play any game, 1,000 Atari games, and even better than humans. And this was really a revolution. But yeah, it was so important, like Atari DQN network architecture with something like this, which I'll try to give a brief explanation, not so much deep, because like we are not reading DQN yet. But yeah, they took last 4 frames as the input, so that they have kind of like an estimation of the velocity and the direction of the ball based on these 4 frames. And then they learned features through deep learning, like they use convolutional neural network, and they have feed-forward layers. And finally, the output was like the action that the agent has to take, like for the ball, for the paddle of the ball. And yes, after that, lots of other algorithms came. Just we had deterministic policy gradient DPG, and then in 2015 we had DDPG, and we had TRPO, GAE, GPS, DDQN, and then PPO, PER, A3C, A2C. There are lots of other algorithms that came after that. And yes, it's just like, can you imagine what the next 2 decades will bring us based on these lots of progress that has been happening from 2015 till now? And to be a part of it, like DRL is becoming a field, and I expect the rate of progress to continue. And then we have like a little gist of the game of Go, which is like enormous branching factor. Like we have from a start point, it mentions that there are so many possibilities. For example, for the game of Go, we have 10 to the power of 170 perfect information states, which is like a lot. Or for StarCraft 2, we have 10 to the power of 270 and stuff like that. There are so many things to cover, and your computational resources has to be so rich and very strong. And yeah, it's all like, it just mentions some of the revolutions. Like we had mechanical engineering, and then we had electricity, personal computers, and here we have artificial intelligence, and different years. And then we have singularity, which is something important. Like many people are actually fearing it to happen right this year, or maybe some years after this, which is the point where the artificial intelligence will reach to the human intelligence. Like we have the human intelligence like this, and then we have this artificial intelligence, and then there's this point, maybe this year, maybe next year, that the 2 graphs will merge, and after the singularity, the like artificial intelligence will just have exponential growth, and it will just go on, and then we will have self-improving AI and stuff like that. And yeah, there's just some history and explanation and the studies that have been done, and maybe the future of AI. But here we are, the suitability of deep reinforcement learning. It mentions that you could formulate any ML problem as a DRL problem, but this isn't always a good idea for multiple reasons. And it just tries to try to think about the gist of your problem first, then make it a DRL problem, because it might not be a very good idea. And it talks about pros and cons. Each of the points highlighted can be a pro and a con depending on what kind of problem you're trying to solve. For example, this field is about letting the machines take control. Now, is this a good or bad idea? And are you okay with letting computers make decisions for you? There's a reason why DRL research environments choices are usually games, because it could be so costly or dangerous to have agents training directly in the real world. Like we have this in autonomous cars, like we have to simulate them, and the training has to be done in a simulation, because doing it on regular environments in a real world will be so costly and also so dangerous. And just it mentions that, can you imagine a self-driving car agent learning not to crash by crashing? And in DRL, the agents will have to make mistakes. Can you afford that? And are you willing to risk the negative consequences, actual harm to humans? Consider these questions before starting your next DRL project. So then we have deep reinforcement learning agents will explore. Can you afford the mistakes? It mentions, oh look, the stocks are the lower they have been in a year, the lowest they have been in a year. I wonder what would happen if I sell all my positions right now. And then it's, yep, let's give a try, sell all. And it's just like the exploration part that might happen. So just having the robot taking control of everything is kind of risky, and you have to think about your problem beforehand. And then it mentions that you should consider how your agent will explore its environment. Most value-based methods explore by randomly selecting an action, but other methods can have more strategic exploration strategies. And finally, training from scratch every time can be daunting, time-consuming, and resource-intensive. However, there's a couple of areas that study how to bootstrap previously acquired knowledge. First, there's transfer learning, which is basically like in neural networks, it's like you train your network based on something, and then you use the trained network to learn something new. For example, you have trained your network to learn on images, maybe like on human faces, and then you try to use the trained algorithm, the trained neural networks, now to have human faces, but with labels, but with like labels of human, like they have learned maybe eye, nose, stuff like that, but now you're using it to kind of like say, okay, this is a picture of James, this is a picture of Anna, this is a picture of someone else. Yeah, and for example, if you want to teach a robot to use a hammer and a screwdriver, you could reuse low-level actions on the, for example, pick up the hammer task, and then use this knowledge to pick up the screwdriver task. Although the environment will be different, but because the robot has some prior knowledge, it will be much easier and faster to learn to pick up the screwdriver. This should make intuitive sense to you, because humans don't have to relearn low-level emotions each time they learn a new task. Humans seems to form hierarchical of actions as we learn. The field of hierarchical reinforcement learning tries to replicate this in DRL agent. And then it mentions deep reinforcement learning's strength. It says that DRL is about mastering specific tasks. So unlike SL, in which generalization is the goal, RL is good at concrete, well-specified tasks. For instance, each Atari game has a particular task. DRL agents aren't good at generalizing. So if you have trained your agent to be a master in breakout game, you cannot expect your agent to be good in Pong. You have to retrain it again on Pong and just Pong. And if you do it both simultaneously, like both Pong and breakout, it might not work. not work as well as you want. So then it mentions that in DRL we use a generalization technique to learn simple skills directly from raw sensory input. And then it mentions that deep reinforcement learning's weakness, like it says that agents need millions of samples to learn well-performing policies. Humans, on the other hand, can learn from a few interactions. Sample efficiency is a problem in DRL that could use improvements. So it's just like an example of that on episode 2,300,000 and something. Like it is like, I almost drove inside the lanes that last time, boss. Let me drive just one more car. And it's just like that. The reinforcement learning agents need lots of information samples. And then it mentions another issue with RL is with reward functions and understanding the meaning of rewards. If a human expert will define the rewards the agent is trying to maximize, does that mean that we are somewhat supervising the agent? And is it something good? Should the reward be as dense as possible, which makes learning faster, or as sparse as possible, which makes the solution more exciting and unique? And this is also an important thing, like designing a reward function to be good is a challenge in reinforcement learning and in inverse reinforcement learning as well. We as humans don't seem to have explicitly defined rewards. Often, the same person can see an event as positive or negative by simply changing their perspective. Additionally, a reward function for a task such as walking isn't straightforward to design. Or something like, can you make a reward function, for example, for scrambling an egg? Like, what is the reward function? How can you design such a thing? And even if you try to make it very simple, it won't be enough. Like, I think there was a paper mentioning that they had this simple reward function designed for a robot to pick something, from the table and move it somewhere else. But because the reward function was so simple, the robot was moving the whole table instead. Like, that was a thing that the robot has learned. And then it mentions about intrinsic motivation, which mentions that intrinsic motivation allows the agent to explore new actions just for the sake of it, out of curiosity. Agents that use intrinsic motivation show improved learning performance in the environment with sparse rewards, which means we get to keep exciting and unique solutions. And the point is, if you're trying to solve a task that hasn't been modeled or doesn't have a distinct reward function, you'll face challenges. And for these unique solutions, you can refer to this paper of OpenAI, Hide and Seek, and that would show one of the most intelligent, like something that the agent goes beyond the humans. And the next part is just about the book. Like the author mentions, let's just have a two-way expectations. He talks about that he has put lots of effort in his book, and he expects to just anyone who's reading this book put the necessary work, do the codes, and not skip any part, because if you will skip, then you might not get the full result at the end. And then it mentions about what to expect from the book, that in chapter 3 to 7, you'll learn about the agents that can learn from sequential and evaluative feedback, first in isolation, then in interplay, as mentioned before. And then chapter 8 to 12, and the core of the RL algorithms. Chapter 1 and 2 are about introductory concepts, and chapter 3 has a concluding remark. And it's like from chapter 3 to 7 is more like the tabular RL, the RL problems that can exhaustively be sampled, and problems in which there is no need for neural networks or function approximation of any kind. Chapter 3 is about the sequential aspect of RL and the temporal credit assignment problem. Then we'll study also in isolation the challenge of learning from evaluative feedback and the exploration versus exploitation trade-off in chapter 4. Last, you will learn about methods that can deal with these two challenges simultaneously. In Chapter 5, you study agents that learn to estimate the results of fixed behavior. In Chapter 6 deals with learning to improve behavior. In Chapter 7, it shows you techniques that make RL more effectively and more efficient. And in 8 to 12, grasp the details of core DRL algorithms. It mentions that in Chapter 8 to 10, the value-based DRL. 11, learn about policy-based and actor critic. And 12 is more like deterministic policy gradient, DPG methods, SAC, soft actor critic, and proximal policy optimization or PPO methods. And yes, that's it. And it mentions comparison of different algorithmic approaches to deep reinforcement learning. Like, we have these different versions of algorithms in DRL and reinforcement learning. Like, we have model-based, and then we have value-based, actor critic, policy-based, and derivative-free. And like, there are some errors that were changed. Like in model-based, for example, we have more sample efficiency, more computationally expensive, more direct learning, and less direct use of learned function. And then as we go through to model-based to derivative-free, we have less sample efficiency and less computationally expensive, less direct learning, and more direct use of learned function. And it says that in this book you'll learn about these algorithmic approaches to deep reinforcement learning. To me, the algorithms are the focus. The algorithms are the focus and not so much the problems. Why? Because in DRL, once you know the algorithm, you can apply that same algorithm to similar problems with hyperparameter tuning, and that's correct. Learning the algorithms is where you get most out of your time. And it mentions how to get most of this book, which you'll need to have a little prior knowledge of ML and DL. You need to be comfortable with Python, code, and simple math, and you must be willing to put in the work, which is the important part. You should know what ML is beyond what's covered in this chapter. You should know how to train simple supervised learning models, perhaps Iris or Titanic datasets. You should be familiar with DL concepts such as tensors and matrices, and you should have trained at least one DL model, say a convolutional neural network, CNN, on the MNIST data. Which, like, if you follow my other videos, which I haven't posted yet, but from the book Hands-on Machine Learning, they do cover these things as well. So you can just always check them as well. However, it mentions that I'm asking people to be comfortable with math, willing to read, and nothing else. The equations I show are heavily annotated, so the people not into math can still have advantage of the resource. And he's right, like I have seen some of the math equations. There are so much annotations that explain every single thing, so it won't be a problem. I also try to cover the math as like clear as possible. And then we have deep reinforcement learning development environment that he mentions that I created a Docker image in several Jupyter notebooks on the GitHub of the book, which is here on GitHub memora/GDRL. The code is written in Python, use NumPy and PyTorch. I chose PyTorch instead of Keras or TensorFlow because I found PyTorch to be a Pythonic library. Well, the thing is, it's good that it's on PyTorch, because if it was on TensorFlow, it would have been TensorFlow 1 back in that area, and now we are moved back to, like, we have moved to TensorFlow 2, which is a challenge. Like, there are not so much good books of reinforcement learning on TF2. But here we are just working with PyTorch. And yeah, that's it. So it says that I want you to learn the RL, so write the RL code. Those who write RL code are more likely to understand RL. And then we talk about Gym, which is a library that provides environments for training RL agents. And some DRL agents make heavy use of CPU, and some of them GPU. So you have to have a good system. Also, you can use Google Colab, obviously, which does provide you with a good system. And then we have a summary. Let's just go with the summary. It mentions that DRL is challenging because agents must learn from feedback that is simultaneously sequential, evaluative, and sampled, as we talked about. And then learning from sequential feedback forces the agent to learn how to balance immediate and long-term goal. Like in the sequential, we talked about this credit assignment problem. We receive the feedback after 5 steps, but we don't know which step was responsible for this reward. And then learning from evaluative feedback makes the agent learn to balance the gathering and utilization of information. And then learning from sampled feedback forces the agent to generalize from old to new experiences. Artificial intelligence, the main field of computer science, into which reinforcement learning falls, is a discipline concerned with creating computer programs that display human-like intelligence. This goal is shared across many other disciplines, such as control theory and operational research. Machine learning is one of the most popular and successful approaches to artificial intelligence. Reinforcement learning is one of the best 3 branches of machine learning, along with supervised learning and unsupervised learning. And then deep learning is an approach to machine learning. It isn't tied to any specific branch, but its power helps to advance the entire machine learning community. And deep reinforcement learning is the use of multiple layers of powerful function approximators known as neural networks or deep learning to solve complex sequential decision-making problems under uncertainty. Deep reinforcement learning has performed well in many control problems, but nevertheless it's essential to have in mind that releasing human control for critical decision-making shouldn't be taken lightly. And several of the core needs in DRL are algorithms with better sample complexity, better performing exploration strategies, and safe algorithms. And yeah, the future is bright. Like there are so many research areas in this field and stuff like that. And yeah, I hope that goes well. So this was chapter 1 overall, the basics and the concepts. And yeah, I'll see you in chapter 2. Goodbye. If you have any questions, just ask them in the comments, and I'll try to be like as time manager as possible so that I can do the weekly video uploads on each chapters and also the HTML. But rather than that, I'll see you again later. Goodbye.